Okay, good evening, everyone. This is Celso Batalha, Astronomy 10, Evergreen Valley College Intercession. So I'm glad that I have four students here, and let me announce to the entire class in case I have two important announcements. First, on Monday is a holiday, campus is closed, and I'm not supposed to work. Yeah, and you're not supposed to come to the chat room, but um, we had, or I thought about scheduling the exam on Mondays, right? So I can't have that exam number two on Monday. So midterm number two is going to be on Tuesday with a retake on Wednesday. Okay. So open and close at midnight Monday, Tuesday, and then open. In fact, what I would do, since it's 2 days in a row, I will allow the midterms to run over the 2 days, Tuesday and Wednesday, two attempts, and then you can take the two attempts one after the other, which I don't recommend. I really recommend that you take some time and review your subject, and then you take it again. So that's the first announcement. On Monday, we don't have class and we don't have chat room. The second announcement is with respect to the proctor. Oh, on Monday I was supposed to do a proctor exam. Then my proctor exam is gonna be on Tuesday. So on Tuesday, if you are planning on coming to the Evergreen to do the midterm number two face to face with me um, at 10 o'clock, then don't go on Monday, go on Tuesday, okay? And I will make sure this announcement goes to the entire class through email. Okay, that's the first thing. The second thing is with respect to communication. I've received few emails from students complaining that I'm not replying to them, um, and sometimes asking questions that are just sending an announcement like, "Oh, I didn't know there was a midterm on Monday," right? I mean, first of all, it's in the syllabus. Second, I announced. So my impression is my communication is going to the junk box. So I will email all of you through the web, my web, to avoid um, your computer to interpret my email or Canvas email as being junk mail. Second, if you are listening to this chat room, check your junk box in case you are not receiving communication from me, because I'm pretty sure I am attempted to communicate with you. But some students are not receiving information and they are quite unhappy, saying that I'm not informing them about issues that goes on in the class. But sometimes I think I sometimes I kind of step back, like now I got late in the class, right? 5 minutes late. I make mistakes sometimes. I'm not saying that I'm perfect, but I try to respond to emails quickly. Sometimes I have students emailing me questions, right? And I don't reply because there are so many students asking the same questions. And what I do, I send an announcement to the entire class. And then I expect that a student to receive the message as, as being a direct reply to the inquiry. It's just to make the system a little bit more efficient. Okay, properties of stars. Let's go to our course. There you go. It's right there. Let's go to the module. So yesterday we studied the sun. After studying star formation, so we know the sun has three main interior regions, and the core of the sun is responsible for production of energy, where four atoms of hydrogen are fused into one atom of helium, and then energy is produced. Gamma rays basically is produced plus neutrino, but neutrino doesn't do much in the sun. And gamma rays spread out and diffuse through the atmosphere and eventually escape. But these gamma rays, as it moves outward, it transfers energy to the gas, and as it does that, it changes slightly its frequency. And this is called diffusion. But you don't need to memorize that. It's just some extra information. So as this energy moves outward, it changes its frequency, the bulk frequency. It changes its color if you think about color rather than frequency or wavelength. So in the core of the sun, temperature is very hot, and then you have gamma rays. In the middle of the sun, the temperature is not as hot, and then you have, let's say, X rays. In the atmosphere with the external region, the temperature is really less hot than it is in the core, and then the radiation assume more of an optical range type of radiation. So when you look at the sun and you see the sun as a yellow greenish star, what you are really looking at is photons, particles of light or energy that was produced in the sun's core, not as an optical yellow radiation, but more like a gamma rays, the most energetic of all electromagnetic radiation. And then it took a million years, according to calculations, by the way, for that radiation to find its way through the atmosphere and eventually escape. And then 8.6 minutes later or so, we receive it here on Earth in the optical range. So why do we see what we see around us? Because we have optical detectors called eyes that were built and evolved to perceive and to interact with the radiation, the bulk of the radiation the sun itself sends to us. So it's an adaptation of life here on Earth, or us, to the energy the sun itself sends to us. Do I have a chat question here? No. Do you want to advise the class about the proctor? I did notes. Oh, thank you, Sarah. Yes. Third announcement. You all are allowed to bring 1 page of notes, and I think I sent that through an announcement as well. The page of notes you can write back and forth, and it's just 1 page, and you have to show that to the camera in the beginning of proctoral exam. So in the beginning of proctoral exam, not all students are doing that. But by the way, you guys are doing great. Don't forget, there is a camera in front of you. This looks like the Big Brother, the cult movie. You know that somebody is seeing you all the time. I freak out to see my students in the computer. It's kind of a funny. Something is not clicking well that way. But don't pick your nose when you are doing exam because the camera is there and I see that. Um, the Proctorio has the camera all the times on you, and the software is intelligent enough to determine if you are looking to the side or if somebody is kind of coaching you or if you are browsing the internet, going to Wikipedia or so to find an answer to questions, or if you are going to your homework and trying to pull up questions. And the software will flag some red marks in case this happened. I made it very light, which means I made the software very light without too many restrictions for midterm number one. And now I have to go to what is recommended as far as restriction for midterm number two. Um, so again, in the beginning of exam, you go to Proctor, you open up, you don't need to download anything. You just need to be in a Google Chrome environment, right? You cannot use Safari, you cannot use Mozilla. It has to be Google Chrome. You have to download that in your computer. And then in Canvas, the extension Proctorio is already there. So when you click on it, it's going to go to, in the very beginning, you need to show your student ID. Give me 3 seconds because I have to verify you are the person that is in the identification and your name is there. Second, you then show your page of notes, and that's what's going to guide you through the exam. Now, I recommend that you become efficiently in creating this page of notes, because the final exam, again, you have one page of notes, but it's encompass a lot of information. So as you get to know more of the subject, you are going to avoid putting a lot of information and summarize in a better way. So yes, thank you, Sarah. Yes, please make sure for exam number 2 on Tuesday or Wednesday that you can bring a page of notes and don't need to rely a lot in memorization. But in spite of that, the grades were fine. You guys did awesome, the grade. I would think the average for exam like that, proctored, is about 50%. Is a D grade, believe it or not, and then improves. And that's why we have extra credit. We have all kind of things going on. By the way, another announcement. Tomorrow we have observatory at Montgomery Hill Observatory, and I already opened a extra credit. Go to your extra credit section. There is one there. Visiting the observatory on tomorrow, right? And then you have to visit the observatory. You have to download some paper. It's right here with instructions on what to do. So print this out, take to the observatory. You have to bring this with you to the observatory because you're going to fill this up there. I will not have copies. Let's be green. I bring too many copies in the past and they ended up being recycled. So print that out, bring with you, and fill it up there and leave it with me. So this extra credit's 10 points and it's due on Friday, right? So it's hopefully the weather is gonna be okay and you have a good time. And if you have dogs and well-behaved cats and kids, please bring kids. The observatory is for kids. It's to bring them some sort of appreciation and curiosity for science and appreciation of technology and how technology can extend our senses so that we can better understand our environment. Okay, so this is a new extra credit that I just posted, and that is tomorrow. So let's go to modules. Oh, more questions. Go back there. What time? Yes, plan on staying in the observatory for 1 hour. I recommend that you arrive at 7 o'clock, 7 p.m., not a.m., 7 p.m., and observatory is going to be closed by 10. Since you have to observe position of certain constellations 1 hour apart, so you have to stay there at least 1 hour. Okay, so observe and then observe again. Okay. All right, so we are then on properties of light and telescopes. No, we are not doing that. We are properties of stars. There you go. Analyzing starlights, chapter 17. So we are in chapter 17. Chapter 17. And we start giving some information yesterday on that. The first information I would like to bring to you is the following. I mean, when you go outside and then you see a bunch of stars, the stars you're seeing are not at the same distance from us. Remember, we rule out the notion of a celestial sphere surrounding us. We don't have a celestial sphere around us. This doesn't exist. We are part of a galaxy. We are about 30,000 light years from the galactic center. And what we see around us with the naked eye, which means if you are in a very dark environment, no parking lot, the moon's not in the sky, let's say you are in Yosemite Park outside and away from any street light. When you look up to the sky, what you see is a bunch of stars. Some of them are bright, some of them are not. And then you can see this fuzziness in the middle of the sky we call Milky Way. Let me see if I can bring this to you. Um, so this is an attempt to reproduce the night sky. I think you guys are already get used to the Starry Night software. But here in the region that I'm showing that has Sirius and Orion and Taurus and Pleiades, this region over here is a region where the Milky Way galaxy is located, or the fuzziness representing the galactic disk is observed. But all the stars that you can see in the sky, like all the stars that you're seeing in this simulation, they are in fact very much close to us. They are up to 3,000 light years away from us. They are not far away at all. For instance, let me take this star over here. See if I can pull up information about this. Position in space, 93 light years. Let me see this star over here. Betelgeuse. Betelgeuse, Betelgeuse, Betelgeuse. Position in space, 425 light years. How about this tiny one over here? Iota Ceti has a name. So what is position in space? 285 light years. So all stars that you can see in the sky, they are relatively close to us. 3,000 light years is not a lot when you understand the galaxy itself has a dimension of about 200,000 light years. So 3,000, not a big deal. It's very close. And as we emphasized in the first day of class, all these stars are not at the same distance from us. They are not in the celestial sphere, in a kind of a simulated celestial sphere. Now, therefore, these stars are at different distances. So why some stars are bright and some stars are not? That was a big kind of a source of dispute and discussion up to the 1800s. Through the 1800s, when astronomy was being developed, and 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 um, and a system of magnitude based on the brightness of the stars were envisioned. So think about magnitude, the name magnitude. Magnitude go up. So apparent magnitude, you can see here, apparent magnitude is a scale that allows astronomers to identify how bright a star is based on a number. And this scale, the apparent magnitude scale, is a logarithmic scale. Now, you might be burning in your shoes thinking, oh my gosh, logarithmic. Who uses logarithm nowadays? Yes, astronomers use. And what's the advantage of a logarithmic scale? I don't know if you studied that in mathematics, but logarithmic scales allow us to convert big numbers into small numbers. Like logarithmic, this operator has different bases. So in the base 10, the number 10,000, the logarithm of 10,000 is the number 4. Right? 10,000 is 10 to the 4th power. And then the logarithm of it is 4. Now the number 100,000 in the base 10 is the number 5. So logarithm of 100,000 is 5. And then a million is 6. 10 millions is 7. So it is a simple scale that takes big numbers and reduce to small numbers. And we know how important that is in astronomy. since astronomy deals with so big of numbers, that scientific notation is very much in use. So how this scale was invented? So what they did, what astronomers do, they take a bunch of stars in the sky that are quiet. They don't vary that much. Remember, we studied yesterday magnetism of the sun, and then we saw the sun undergo several changes in flux and activity because of its magnetism. The magnetism of the sun changed in a time scale of 11 years. In fact, 22 years, and with the polarity that changes every 11 years. So in this apparent magnitude scale, astronomers identify several stars that were quiet, and then they calculate with very good precision the amount of energy, which means if you take the light these stars send it to us and we detect here on Earth, so measure that light and then convert that measurement to a number, right? Um, Astronomers and physicists, they can quantify energy quite well. For instance, I have a good example. You go to the supermarket and you look at your food, you want to buy some food, it has a unit of in there called calories. So calories is exactly what? Well, the calories that you read in the label, in the food label, is related to amount of energy that food brings to you. So if you burn that energy as you eat, that's great. If you don't get fat, that's the reality, right? So exercise is good. Don't forget to do your exercise. You coach your kids to be active and healthy and have a healthy lifestyle. So very important. But going back to physics, so energy in physics is quantifiable with certain units. So calorie is a unit of energy, joule is a unit of energy, and energy per unit of time is called power. So power in physics, not powerful. Powerful, man, some people say, oh, our president is powerful. Uh, I mean, in physics, this is not powerful. I, I, I mean, the president of the United States is always powerful, right? So I think I should start being quiet. So power in physics is not what we call powerful, right? Power in physics is how much energy can you convert in certain amount of time. Is a very quantifiable and measurable type of quantity, and there are several units of energy depending on which system you are operating. Now, so what astronomers do, they measure the amount of energy the stars, these quiet stars, send it to us. And to one of them, they take this energy, which is a very small number, 10 to minus 14. 10 to minus 14 in this unit of energy, or 10 to minus 13. It's a very small number because the stars are faint. They are so far away. They have too much energy, lots of energy, but they are so damn far away that just a slightly amount of that energy we ended up receiving here. So, and that energy, believe me, is very small, 10 to minus 13, 10 to minus 14, which means 0.0000013 zeros and then a number. So just to give an idea how negligible that is. But what astronomers did is they took these quiet stars, they call standards, and they convert their energy to zero. And among these stars, Vega is one of them. Vega is a star that astronomers measure the energy of Vega. Is a bright star, and they say, okay, from now on, Vega has a magnitude that is zero in the logarithmic scale, which means they took the energy that Vega sent to us, and I'm making a number, let's say 10 to minus 10, 10 to minus 10, and they apply a logarithmic scale. Well, 10 to minus 10 logarithmic scale, the base 10 is negative 10. And then negative 10 became 0, right? And then all the other stars are compared their magnitude or their brightness to Vega. I know it's complicated, but let me tell you what you need to know. What you need to know is this. After everything is done and calculated, the stars range in magnitude at very nice numbers. And then you can see them here. Let's say Polaris has a magnitude that looks like in the scale 2.5, right? Now, the limit to what you can see with your naked eye is the magnitude 6. And also, be attentive here because the bigger the number, the fainter the object is. Look at the sun. The sun has a magnitude scale in this magnitude scale is a number that is negative. It's so small that it becomes negative, and not only that, it's a very small number, negative 25. And the sun is the brightest thing in the sky we know. Why? Because the sun is a star, first of all, and it's really close to us. It is in our backyard, for God's sake. The full moon, the second brightest object in the sky, has an apparent magnitude of about negative 12 or so. And that's how the magnitude scale goes. So the other thing I would like to call your attention, and this picture here shows quite well, is that stars come with different colors. In astronomy, the cooler the star is, the redder it is. The bluer the star is, the hotter it is. And let me show you an animation that might illustrate this. Sorry, not this one. Where is it? I thought I had to save it. No, no, no. Launch meeting. No, it's not this. It has to be this one. Oh, there you go. So look at this. Here's a simple example. You have a conductor that it has a circuit here, basically, right? And what we're gonna do, we're gonna set a current going through this thing. Hey, Alberto, how are you?
What's up, Professor?
Good, good, good. I can see you.
Good, good.
Okay, so
you can't?
What?
Oh, I have a quick question. Just one quick question.
Oh, you know I'm taping this, right? The entire universe is looking at you now.
Oh, really? Oh, yes. I'm at work. It's for the extra credit tomorrow.
Yes, for the observatory. What about?
Yeah, what time? ¿A qué hora es?
Say it again.
Or what time is it at?
Oh, it started at 6 o'clock. Oh, well, we will start setting up things at 6 o'clock, but I'm recommending people to arrive at 7 o'clock and plan on staying.
How late can I get there?
10 o'clock. I'm falling asleep. It passed my bedtime.
Because I get off at work at 9, so I was wondering if I could just show up.
Oh, show up there. Just go. Yeah, we'll stay there for you.
Okay, cool. Thank you. Obrigado.
Obrigado, de nada, man. De nada.
Okay. Boa noite. I have to go back to work, Professor. Thank you so much.
Okay. All right. Sounds good.
Okay.
All right. Bye.
Bye. Thanks.
Bye. So here, what is happening now, the circuit is allowing current to go, and the metal connecting these two part of the circuit is heating up. It's becoming hotter and hotter and hotter. And you notice the color is changing. So the temperature changes, but the color changes too, to the point that eventually it breaks apart. And then the circuit closes like a breaker, circuit breaker, right? When you have an overloading current, some part of the circuit melts down and then prevents and shields the circuit from further damage. Let's do it again. So you start the current going, the temperature starts with a dark red, becomes bright red, and then really yellow, and the temperature keeps going up, and then you can see in this black body curve here, to the point that eventually the circuit breaks because the metal itself melts. So stars are hot, and the hotter the star is, the bluer it is, the white it is. And the stars that are red are kind of low temperature stars. And the black body radiation, the black body curve, and I know is a challenging thing to understand this concept without studying physics. But what you need to know is that black body radiation is the following thing. It's not the radiation that is being reflected off the walls in the room you are. So if you happen to be in a room now, and then you can see colors around you, you can see red, you can see blue, you can see purple. So all these colors, they are not the result of the radiation the object itself is producing. Those colors are light reflected off the surface of this object, because let's say the sun has a white coloration, right? A white light. And white light is a combination of light of all possible frequencies. So when this white light of the sun hits certain surfaces, like a leaf, right? The tree leaf. So what the tree does, it retains everything except the green part of that radiation. And then the leaf itself absorbs the infrared, absorbs the ultraviolet, but rejects the green. And then we see trees, the leaves are green. So I have a red coat, and I'm looking at it right now. So that coat is red because the light that comes out of the light bulb, the filament in my room, is hitting, is touching the surface of that coat, and everything else is being absorbed except the red radiation that is rejected. And then when I look at it, I see it as red. Now, imagine an exercise that I turn off the entire light in my room. I can't see anything because my coat is not radiating red light, right? It's not intrinsically putting out radiation. Not like here, in this exercise, the body itself is radiating light, and the light is started with a dark red, bright red, and then white, yellow, and then melts, right? Or yellow, white, and then melts, um, indicating a tight correlation between colors and temperature. And that is what the Wien's law we study in this chapter exactly tells. Okay, how do we study the properties of stars? We study the properties of stars because in this picture here, before we go there, in this picture here, see this yellow star right here. See this other yellow star, this other yellow star. They are cool stars, whatever. This blue star over here is pretty much a hotter star. Spectral classification is the process by which we can use spectroscopy to determine properties of stars. There is a very nice way to memorize the spectral types nowadays. It goes from O, B, A, F, G, K, M. Easily memorized. You can read this in all books that I know of astronomy. Even in Brazil, it was given that way. O, B, A, fine girl or guy, depending on what you like, kiss me. See that? Simple, right? O, B, A, fine girl or guy, kiss me. In fact, the spectral classification goes from O stars are the hot stars, M stars are the cool stars. Remember, there is a extra credit going on of an exoplanet around an M star. Now you know what an M star is. An M star is a cool star. It's a very cool star, one of the coolest stars there is. And Mother Nature likes to create small stars, which are cool stars, rather than big stars. Big stars are created, but when they are formed, they don't live for too long, as we will learn in stellar evolution. So spectral lines are typical of certain elements like hydrogen, helium, beryllium, lithium, calcium, magnesium, zirconium, vanadium, titanium. All these atoms, they have transitions when the electrons in their atoms change position. They either absorb light or they emit radiation when they undergo these transitions. And by observing this net of transitions and the resulting light or net of this transition, astronomers can identify what is called lines. So these lines are typical of certain elements, which allow astronomers to know which elements, which chemical composition stars have without going there. So the only thing you do, you take the light of stars and then you make a rainbow of the light, and then with very good precision and technology you identify transitions, and then you compare these transitions with some reference, and then you can identify which sort of chemical elements the stars has. Not only that, depending on the intensity of these lines, you can also estimate the stellar surface temperature. So again, spectroscopy is an important tool astronomers have that enable them to investigate stellar property like rotation, chemical abundance, surface temperature, gravity. Um, Low gravity stars, they have these transitions indicating lines that are very narrow, very deep and narrow. Whereas the stars that are of high gravity, they tend to show broader type of lines. The stars that rotate fast, they in general show a broader lines. So also astronomers can use this spectroscopy to determine the dynamics, the speed, the velocity, the projected velocity of stars, as you can see in these lines. Those are the main properties I would like to talk about it. I will in stellar rotation too. When the star rotates, um, part of the star, let's say the left hand side of the star, move towards you, while the right hand side of the star moves away from you. So you have a Doppler shift that broaden the line as you observe, and astronomers can take this broadening and use and measure the projected rotation of stars. So again, chapter 17 is important because it gives us tools that enable us to better understand how astronomers do their jobs. So we don't invent things. We observe the light. Light is the ambassador. Light is the carrier of information from the universe towards
Alert us. From System UI server. Low battery.
Thank you. Thank you. You are so
Alert
kind.
From.
Okay, don't need to repeat that. Man, that's inconvenient, but it's better if I put some cable on it. But basically, that's it. Spectroscopy, photometry, they are the tool of astronomers. You don't need to go to the stars. The stars come to you through the light they emitted. Okay. I know on Monday there is no class, but I will be online. I will open the computer at 7 o'clock and I will review the subject for the midterm on the following class. You don't need to come, but if you come, it's gonna be great. Uh, uh John, uh, uh, John Paul. Oh, John Paul, John Paul. Did you do midterm number one? I don't think I have a grade for you. The midterm number two is gonna be on Tuesday. I will be there face to face on Tuesday at 10 o'clock, because on Monday we don't have class. But if you want to do the proctor part, you can do at home with Proctorio. But I have some students I don't have information about grades, not a lot, as if they had missed midterm number one. And I have the impression you were one of them. Do you have a grade for midterm number one? I can't open now or everybody's gonna see. I can't do these things. But check your midterm number one, make sure everything's fine. If it's not, just blast me a mail. Okay? Any other question? All right. So, uh, oh, uh, John Paul, uh, send me a mail. We can talk. Oh, okay. All right. Yeah. Why don't you send? Now I understand. So send me a mail and we can figure something out. Okay. Just let me know. Okay. All right. Okay. Good night, everyone.